Welcome, everybody. It's a great pleasure to have Phillips here from UIUC. He's a professor there, and he's a leader in the theoretical study of quantum phase transitions and strongly correlated systems, specifically novel phases in 2 dimensions, and these correlated systems known as high-temperature superconductors. And this is, you could say, the problem in correlated systems, is understanding why there are these exotic materials that exhibit either insulating behavior, Mottness, and yet can be high temperature superconductors when they're doped. And I'd say, yeah, so what's interesting and what I'm finding out today is he crosses the boundaries of our department. He uses particle physics ideas in condensed matter and is certainly not shying away from the hardest problems. He served the APS in many, many roles and has many honors. He wrote a book about solid state physics a while back. He's a fellow of the American Physical Society, a fellow of the American Association for the Advancement of Science, and John Guggenheim. He has a John Simons Guggenheim Fellowship from 2015 and many, many other honors. And today he's going to tell us about beyond BCS and an exact model for superconductivity and Mottness. So it's a pleasure to welcome you here.
Thank you. I've made good friends here. One of them is David Greer. And I haven't seen David in ages. And the first thing he said to me is, "Philip, you're talking about what?" Exact theory. Yeah, sure, Phillips. Okay.
Actually, I said, yeah, right.
Yeah, you said yeah, right. Yeah, okay. This is what I'm going to talk about. I never thought I would be putting exact and Mottness and superconductivity together, but I have. And you can tell me how I have succeeded. Okay, so this work was published in a couple of Nature Physics papers. We finally got it right in the second Nature Physics paper, and then it was explained fully in the long PRB. Is there a pointer, or just have to use my?
There
No, it's
might be
fine.
a light.
This is stick.
The stick has been stolen.
There you go.
There's a stick there.
Well, the extensible stick.
What a New York City thing to have in the recording. New York City.
Is that working?
David. Is there a stick? There's a stick right here.
There's a stick here.
Yeah. Perfectly. Yeah, perfectly fine. Okay, 80 retracts. Okay, so got it. Okay, as you know, there's this problem in our field. It's been around for a very long time. I'll tell you how far I got. Okay, so my collaborators, 2 students, Luke and Jin Chao, my current student, a postdoc, Edwin Huang, and then a math faculty member, Gabriele Lanave. Okay, so good. So superconductivity began in 1911, ostensibly. And with this observation, the resistivity dropped below a point where they couldn't measure it. And 2 years later, this phenomenon won a Nobel Prize. And it was a long mystery as to what was going on until several former colleagues at the University of Illinois did the following. Cooper had the great intuition to say, let's ignore all the electrons below the chemical potential and just pair 2 of them up, and this operator, P dagger, creates 2 electrons with opposite spin and momentum P and minus P in a state outside the chemical potential. And he simply asked the question, what's the ground state of this system? So I have a full Fermi C, 2 electrons outside with an attraction between them. And what he noticed is that this system forms a bound state below the chemical potential. And that's impossible because there are no states below the chemical potential. And hence what this says is the system has to reorganize itself into a new state of matter. So this is the Cooper instability, and it started the whole thinking that turned into BCS theory, which everyone knows. It's one of the most successful theories in all of solid state physics. Okay, And so what this says is there's a condensate, and this is what BCS used, and there's some amplitude in a phase. Now, one of the questions you'd like to know is, how valid is any of this? Because you ignored all the interactions between the electrons below the chemical potential. Okay, so what about the repulsions? Well, this is what John Bardeen told his students. Just think about p squared over 2m. This is exactly what I'm told this is what he said. He told the students, forget about the interactions, let Landau solve that problem. And well, that's basically what Landau, it wasn't Landau, okay, it was, but see, you asked the question, how do you destroy a Fermi liquid? It turns out it's hard to destroy a Fermi liquid. Now, you might think you can destroy a Fermi liquid by adding on repulsions. So you have some action that includes the repulsions between the electrons. As long as those repulsions are short range, you will never destroy a Fermi liquid. And that's because those will all flow to zero. And you'll still get a Fermi liquid, and it's because these operators are all irrelevant relative to p squared over 2m. Okay, and that's why it all works. Okay, so Fermi liquid theory is essential to BCS theory because it's anchored on this non-interacting picture. And they didn't leave anything out. Now, Bardeen didn't know this. It's sort of something that always sort of puzzles me. How could he have known this? You know, you don't know this. But anyway, it was the right answer to forget about it and play golf. And so this is basically the picture we have about a Fermi liquid. You turn on repulsions, as long as they're local, you will always flow to a Fermi liquid. The only thing that destroys a Fermi liquid is this pairing interaction that Cooper came up with, and it describes a whole new state of matter. And to describe all that state, you need the BCS theory. Okay, now, yeah, and there's one number I want you to keep in mind, and that's 2 delta over TC in BCS theory is 3.5. So just remember the number 3.5. Okay, so this all works because Fermi liquid theory is a fixed point, and fixed points are nice because they can organize our thinking. And we know we're right because there's nothing relevant that we've thrown away. Okay, so the question arises, is there anything beyond this picture? Is there a quartic fixed point, which describes interacting systems? And what is the superconductivity that comes out of those systems? Okay, this question is on a lot of people's minds because of the copper oxide superconductors. And what is new about these materials is that they're not Fermi liquids. They are Mott insulators. And Mott insulation started with Mott, who was worried about nickel oxide. The general statement about metals and insulators is metals have empty places to put electrons. Count the number of electrons, you count the number of states. If the number of electrons is less than the number of states, which isn't the case of nickel oxide, it should conduct electricity. It does not do so. A lot of these oxides, that's the case, but they're very good insulators. And so Mott came up with a picture. It's a real space picture. And he said for electrons to move from one end of the sample to the other, they have to be able to hop. But what if the energy of hopping is, he said, perhaps this costs some energy. And so what if this energy is much bigger than the hopping? Could it be the case that without doing anything to the system, a gap forms in the spectrum, and right at the chemical potential, there are no states there? If there are no states there, and that's where the chemical potential would be if you were to turn on an electric field, you would see no transport in the system. And you're doing this without changing the size of the Brillouin zone. So there's no symmetry breaking. I'll get to that in a little bit. And this is entirely a real space picture, which will be important in everything that I tell you. Okay, so this is what Mott said. Okay, now this model that I've written down has a certain name. I haven't really written it down, but let's say the picture is worth 1,000 words or 1,000 equations. This is a colloquium, so there are no equations, so there are very few. But this model has a certain name, it's the Hubbard model. And there are only two parameters in it, the hopping and the repulsion, and two electrons sit on the same site. Okay? So that's the problem ahead of us in high temperature superconductivity. You have to solve the Hubbard model. You have to illustrate a Cooper instability. And let me tell you the progress so far. Now, neither of these problems is solvable. Okay, so what is the progress? Well, the progress goes by lots of acronyms. I won't tell you what these are. But because the problem is insoluble, there are lots of disputes. And let me tell you about one of the disputes which has influenced my thinking profoundly. So it's a dispute that involves Bob Laughlin and Phil Anderson. Okay, and they wrote papers in 1997 that were sort of not separated by too many months. And this paper excoriates the whole field for even thinking about Mott insulation. And he has a series of sentences which begin with nowhere, 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 nowhere. And the point is, nowhere can one find any precise terminology of what you mean by Mott insulator. Okay, that's Bob Laughlin. He doesn't hold back. And Phil Anderson said this statement would be ludicrous if it were not so influential. But then he also said this: it is the tragedy of Mott that although he most certainly won his Nobel Prize for the Mott insulator, Slater, who couldn't think clearly about finite temperature, won the publicity battle. Okay, what is going on here? Okay, so here's what's going on here. And I have to say, Bob Laughlin has held the field back for quite some time because of this paper. Here's what Bob Laughlin was talking about. Everyone knows a half-filled band should conduct. If it doesn't, it's doing so for a simple reason. Let's just say what's going on is that the atoms don't do this. They in fact reorder, and they have two different colors. So you have a periodic arrangement in which you've changed the size of the unit cell. You have 2 atoms per unit cell. 2 atoms per unit cell, you should generate 2 bands. And you've essentially gotten rid of the Mott problem. Because now this lower band is full because you have 2 bands in the system, and this half filling is now full filling of this lower band. This requires a symmetry break and changing what you mean by the Brillouin zone. There's no Mottness here. You've gotten rid of the Mott problem. And this problem is solvable with some diagonalization of some mean field Hamiltonian. Okay, so it's at that point I said, well, these are 2 very smart guys. Let me look at the difference between them. Okay, so the difference between them is what I call Mottness. Okay, and if everything that Mott was talking about is exhausted by the explanation that Bob Laughlin came up with, there should be nothing left over. There should be no explanatory residue. So the explanatory residue of this debate is what I call Mottness, and it's delineable by one phrase, by zeros. And zeros, it turns out, is the zeros of the determinant of the real part of the single particle Green function. And it's very modular. In this case, it's non-zero. In this case, it's 0. Okay, so I'll tell you about this quantity, and I'll show you how this comes about. So Mottness isn't just some airy-fairy idea. It's very quantitative. It's whether a certain quantity is equal to 0. Okay, so the student meeting I had was very helpful because we went over the two things you do in math. You either count or you integrate. And most people like to integrate, they can't count. I kind of prefer to count, actually. So let's count. Okay, so let's count the number of particles. So there's a simple way of counting particles. You just put numbers on them and you count, right? Okay, so well, that's not very efficient. Okay, so is there a more efficient way of counting? Yes, there is. And this is this theorem by Luttinger, who spent, I think, his whole career at Columbia or Bell Labs or something like that. Okay, good. Now to count, I'm going to look at this function. It's just 1 over an energy minus the energy of a particle, or energy of a state with momentum p. Okay, so if this probe energy encounters this denominator is 0, and this thing goes through an infinity. Okay? Okay, so let's say that there's one of these things right here. Let's look at the behavior of this function in the vicinity of that point. But in the vicinity of that point, this function changes sign. And here it's negative, and it goes off to negative infinity. Here it goes off to positive infinity. Okay? This is the standard pole type excitation, and there's a sign change here. If this represents the energy of a particle, if you count the number of times you have a sign change, that should tell you the number of particles multiplied by 2. Okay, that is Luttinger's. Okay, that's one part of Luttinger's theorem. Luttinger's theorem says you have 2 because each state can have 2 electrons in it. Theta, the Heaviside stub function, you're counting the part of it that's positive, and the argument of this function is positive. Okay, now, one of the ways a function can become positive is by having a pole type singularity. But that's not how we all learn functions become positive. We knew they could become positive the moment we learned about negative numbers. They just change sign, right? They can just change sign. These are called zeros. Okay.
Somebody's not
It's a
muted.
Zoom, probably somebody's not muted.
Huh?
Somebody
Oh,
who's
okay,
listening
okay.
on Zoom comment.
Okay, it can just change sign.
You can mute others. Can you back for Zoom?
Somebody's not muted.
Mute thyself.
Or someone's trying to ask you a question.
Or someone's-
Or someone asking a question.
Сурачу поехали.
There's a mute all at the bottom, Andy, in the middle.
Mute all, they would,
Yeah.
that will mute us too, right?
Yeah, not unmute
So
yourself.
then you
Okay.
can
Oh,
Okay,
that was fun, hold on. Now we have to unmute ourselves, right?
No, you're
we're
unmuted.
fine,
You're
fine,
good.
fine.
Okay, good.
Yeah.
I'll get rid of this.
okay. It turns out Luttinger's theorem is counting all of these. It's counting zeros plus things that look like this. All of this determines a physical quantity according to Luttinger, and I put theorem around it because it turns out there is no such theorem. The statement is wrong. That all of these sign changes are related to the physical charge in the system. Okay, so that's how you would count according to Luttinger. Count the number of sign changes. Okay. And this 0 is the determinant of the green function equaling 0. Okay. Now, how do zeros obtain? Okay, the zeros obtain because, so let me just construct the real part of the green function. And let's just do it from the imaginary part using Kramer's Kronig. So let's say the imaginary part of the green function looks like this. It's entirely a positive function because it's the density of states. And let's take this moment. over omega, using this is the Kramers-Kronig relationship, I'll construct the real part. We see immediately what's going on. This is entirely positive. The denominator can change sign, which means there will be a balancing act between the positive and the negative parts, which means this thing can actually go through 0. But what it means is that you can't throw away the higher or the low energy parts of this problem. Both are telling you something about the excitations at 0 energy. What is the behavior of this function at 0 energy? Okay, these are zeros, and it's inextricably related to a gap in a strongly correlated system, and this is in a single band. Okay, in what Laughlin is talking about, this never happens because when you break the symmetry, these two things are in different bands, and there are no zeros. Okay, the Mott problem is all about zeros. Okay, so zeros are telling you the propagator is 0, which means there is no propagation. It's telling you about the breakdown of the particle concept. So anytime there's zeros in a problem, there's something that does not have any description in terms of the stuff you originally wrote down your theory in terms of. Okay, and that is Mottness. Okay. Okay. So now you understand what Mottness is about. You ask the question: what is the minimal model for Mottness? We're told it's the Hubbard model. We can't solve the Hubbard model, and that's why this field has made very little progress. So I just want to throw away the Hubbard model and go back to basics and ask the question: is there something else that contains all the information of the non-trivial physics of zeros, but still gets at the Mott problem? Okay. Does everyone understand where I'm going? Okay. Okay, now, to do that, let's call on Phil Anderson again. Phil Anderson noticed something which is intrinsic to the Mott problem. If you look at this spectrum, for removal and addition of particles, or just spectral weight, in the cuprates, it's asymmetrical. This slope here doesn't equal the slope here or here. So there's a whole particle asymmetry. And Phil said, I remain baffled by the almost universal refusal of theorists to confront this evident fact of whole particle asymmetry head on. Okay, so if you're trying to construct a theory that has the content of the Hubbard model, but none of the complications, you should at least build in this particle hole asymmetry. Okay, so let's go back to, let's take a closer look at Fermi liquid theory. So Fermi liquid theory is a non-interacting theory. I've written it in a slightly more complicated fashion here, but the important thing, it's a quadratic theory. You have psi dagger, just a quadratic theory, non-interacting electrons. But I've written it in a fashion that shows a symmetry between the spin and the charge sector. Okay? So there are 4 objects. There's this, and then the Hermitian conjugate. Okay, all that stuff renormalizes to 0. There are 4 objects here. Okay, and what Anderson and Haldane said in this paper in 2000, and they're asking the question, how do you really break a Fermi liquid? They said, well, if you have 4 objects, the symmetry group for a Fermi liquid is O4, which is the most unbiased statement you can make. And O4 has 2 sort of subsets. One are proper rotations, improper rotations. Proper rotations leave nothing unchanged. Improper rotations do. Okay, the proper rotations, they have a determinant of 1, and this is SO4. And this is the thing that we have written it like this. SO4 is SU2 cross SU2. And that means you have two SU2s, one for the spin, one for the charge, and they are equivalent. And that's why Fermi liquids have particle-hole asymmetry, because of this. There's also something else going on, the improper rotations. The improper rotations have a determinant of -1. And those come about from just the quotient of O4 with SO4, what's left over. And that's a Z2 symmetry. Okay?
You know, I may have misheard you, but I thought you were saying in the first case with proper rotations in SO4 that produced the asymmetry.
No. SO4 preserves it.
Great, okay, good. I thought.
Right. No,
I
it
didn't,
has
I must have
completely,
misunderstood you.
yeah, absolutely.
Okay, thank you.
Okay, good. Okay, what is going on with the improper rotations? Okay, so let me construct this matrix because it has a determinant of -1. But then I need to act on it. I need to act on something which is going to tell me why it gives you a -1 or what is resulting from the -1. Okay, so here are my 4 objects. Okay, now to show you how this matrix acts on them, I'm going to take sums and differences of these, and I'm allowed to add and subtract in a colloquium. Okay, I'm going to take sums and differences of these to get real operators. Okay, just go to the Majorana basis. Okay, see here, I just added this to this, that's that. I took the difference, that's this one. So all of these are real now. Okay, now I can act my matrix on this. Okay, now this matrix has a determinant of -1. Okay, there's only one minus sign here. Let's act this on this. Okay, if I act this on this, what does it do? It interchanges these two. Okay, so it's interchanging a hole with a particle state for only one of the spin species. Okay, so this is a particle hole transformation. Okay, now that Hamiltonian for a Fermi liquid is not invariant under this transformation at all, except at one particular point. If you look at EP equal to EF, the Hamiltonian is equal to 0, which means I can make any transformation I want. In particular, I can make this transformation, which means for the electrons right at the Fermi surface, or right at the chemical potential, the part of this which is the same is this transformation. So their point is, aside from the standard symmetries Fermi liquids have, there's another inherent symmetry, this Z2 symmetry, and that's what makes Fermi liquids special. Okay, that's the particle hole symmetry. Okay, you can make this transformation and you haven't done anything. The Hamiltonian is equal to 0. Okay, now, so how do you destroy Fermi liquids? Now we know. You have to destroy the Z2 symmetry. Okay, so how do you destroy the Z2 symmetry? Well, you can add a magnetic field that couples to N, but I don't want to do that. I want to preserve time reversal symmetry. Okay, the simplest thing to do is to add this term. Because under the Z2, this thing changes sign. One of them goes to NP down, will go to 1 minus NP down, in which case I will have changed the sign here. If I add this term, this cannot describe a Fermi liquid, because when this term vanishes and you're right at the chemical potential, you will have changed sign. This model inherently breaks the particle hole symmetry of anything that was at the chemical potential. Okay? Now, this model is trivial. because this term commutes with this one. So this model is highly solvable, but it's non-trivial. I should say it's solvable, it's not trivial. Otherwise I would be telling you about it, okay? This model is that this odd under Z2. If you look at the scaling dimension of this term, it's -2. It's only one momentum integration. Just do all the power counting, it's scaling dimension -2, which means it's a hugely relevant operator, which means it's going to take you away from the Fermi liquid fixed point. Okay, and so it's irrelevant perturbation. There has to be a new fixed point. This is the Hatsugai-Komoto model, which was actually written down in 1992 before Laughlin made his statement that there is no such thing as a Mott insulator. But it turns out this describes a Mott insulator. So it's exactly the Hubbard model, but in momentum space. Okay, which means if you were to construct this in real space, it's a highly non-local model, just like the Sherrington-Kirkpatrick model that Dan Stein has studied. Okay, in fact, that's how they came up with this. They were looking for a Sherrington-Kirkpatrick type of model of a Mott insulator. That's hugely solvable. Okay, now that model is the mean field theory of the Edwards-Anderson model. This is the mean field theory of nothing. What I want to try to convince you of is that this is a fixed point that even includes Mott physics. Okay. So the general HK model, it looks like this. There's only one momentum here. If you were to Fourier transform the Hubbard interaction, it would have 4 different momenta. It only has one. Okay, and that's why it is such a hugely relevant operator. Okay, and it's solvable, and here's the green function. The green function is the sum of 2 different terms. Anytime you add 2 things together, they can give you a 0. In fact, that's why. You've changed the spectral weight from being just at one point to being at 2 different points. And hence you've broken this one-to-one correspondence of Landau. And this is the lower Hubbard band. And the other thing is the upper Hubbard band. Okay, so we have a very well-defined prescription for what we mean by the lower and the upper Hubbard bands. And the weights of these bands depends on the occupancy, which means these are not non-interacting bands like the conduction and the valence band are. Okay, these are really non-trivial bands. But we know how to construct them. Okay, which means we have zeros. This has a Mott transition. Since we pay an energy cost to U anytime we put 2 electrons in the same K state, if U is bigger than the bandwidth, this band lies up here, only this one, and this one is way down here. None of these cross the chemical potential. The system is an insulator. There has to be a surface of zeros between them because these 2 poles are now symmetrically located relative to the chemical potential. And this is the surface of zeros. Okay, this band is created by this kind of quantity. Now I define this because this is going to be relevant later on. This band has to be either singly or has to be singly occupied or empty, which means if there's something here, there can't be something there at the opposite spin. So this is already deviating from this being a single particle band. And likewise, the upper band has to have something already down here, which means it's this multiplied by that, meaning this has to be double occupancy. And that's how these things are separated. Okay. And if you change the doping, so if you just change U and W, this band drops below. There's a region here now which is singly occupied. So now you have singly occupied states below the chemical potential. this cannot be a Fermi liquid. Fermi liquids have doubly occupied states up to the chemical potential, and that's it. The reason why you have singly occupied states below the chemical potential is that every state now costs an energy U if you were to doubly occupy it. Okay, so we have a non-trivial model. It has empty states, singly occupied, and doubly occupied states. Okay. And this will have to describe a metal because the chemical potential below. Okay. Okay. Now, one question you can ask is, are we wasting our time? Okay? Because this model is so different than the Hubbard model, it doesn't have any local interactions. Okay? So if you were to take the HK model and add a local perturbation, or something short-ranged, would you destroy the HK physics? The answer is no. There is no local perturbation that you can add that would get rid of the Mott physics here. All of these operators have scaling dimensions bigger than -2. In fact, there's nothing that you can write down that has scaling dimension smaller than -2. Except you wrote down something ridiculous which would change the nature of the correlation functions in the basic HK theory. Okay? So there's nothing that you can add. You can go and construct the beta function exactly, and it all scales to 0. Okay, which means this really does describe a quartic fixed point. Okay, now, what I want to do is look at the original paper by Anderson and Haldane. It's just a 1.5 page bundle of joy. And this is one of the lines in the paper. Okay, now the question I want to ask you is, they said this short-range repulsive interaction maximally violates the Z2 symmetry, and hence this can't be a Fermi liquid. That statement is very true. But there's something wrong here. They didn't specify, there are no subscripts here. Which means it's neither a short-range interaction nor something in momentum space. Okay, I gave the summer school at Princeton this summer, and I said, Duncan, there are no subscripts here. And he goes, yes, there are no subscripts there. And the reason there are no subscripts there is they suspected the answer didn't matter. Okay, but they also knew that the Hubbard model has a completely perturbative regime. And they're trying to get around that whole problem. But ultimately, they knew what they were talking about was a problem in which this interaction was in momentum space. But they were unaware of any model, including they were unaware of the Hatsugaya-Komoto model, which is basically the Hubbard model in momentum space. Okay, so the question I want to ask is it true that it doesn't matter what you put there? So is it the case that as long as you're in the non-perturbative regime, it doesn't matter that Hubbard is equal to HK? Okay, so let me tell you what Hubbard leaves out. This is what Hubbard leaves out. The only thing I want you to, this is what HK leaves out, which is in the Hubbard model. If you count the number of empty sites, okay, I'm just going to evolve this. You can have lots of hopping. And as you see, the number of empty sites is not a conserved quantity because no eigenstate of the Hubbard model has a well-defined number of particles on each site. Okay, so I've generated two empty sites, which means there is mixing as a result of the hopping between the upper and the lower bands. That's called dynamical spectral wave transfer. And it's coming about because these two terms don't commute in the Hubbard model. That's the simplification that is made in the HK model. So we get these two bands, they're well separated, and the spectral wave moves like this. but there isn't this dynamical mixing between them. Okay, so let's focus on that. And is that enough to kill any analogy I have in the HK model and the real physics? Okay, so can HK give rise to dynamical spectral wave transfer? Okay, this is what you would have in the HK model right here, this solid line. This stuff here are all the T over U corrections, and they're present. This is what's going on in the Hubbard model. This is this classic paper by George Sawatsky, which shows clearly dynamical spectral wave transfer is present. Okay, is it possible to get this in the HK model? Okay, so all you need to do is, rather than just this single site basis, go to a two orbital basis where you have hybridization that completely eliminates the inherent degeneracy of the singly occupied sector in HK, because there's a well-defined ground state, and you will be destroying the commutativity between kinetic and the potential energy, and as a result, you'll generate dynamical spectral wave transfer. Okay? So this is what you get in just pure HK. Now you have the dynamical spectral wave transfer. Okay, now I put to you, what have we left out? Two models look pretty much the same. This is why I think HK is a fixed point. It does not differ in any profound way from the Hubbard model. Okay, now with that, I now want to turn on superconductivity to see if there's a Cooper instability in this problem. Okay, Cooper instability. What you need to do is look at the HK model and turn on the term that Cooper turned on. Two electrons outside the chemical potential. Do they condense into a singlet state and form a bound state? Okay. It's harder to do that here because the HK model keeps the electrons apart. Okay. So this is the term I turn on. I turn them on right there outside the chemical potential. And I want to compute this quantity. And if you have a bound state, this thing has to be negative. Okay, well, here's the answer. There's a Cooper instability. I'm plotting here EB, which is the negative of this quantity, and it is non-zero. This is as a function of the coupling in the Cooper channel. Okay. Now it's fine to show that there is a Cooper instability. What you really like to know is, what is the ground state? Can you calculate the superconducting susceptibility? In this model, you can do so exactly because the K states don't mix. Okay, so we went and computed that, and you find it looks like this, which means when this equals 1, there's a divergence. And that will define TC. So here is this function. This is chi0. Yeah, chi0 is right. Yeah, so this is chi0 is right here. It's growing as you lower the temperature, just as in a Fermi liquid. The chi0 for the HK model is growing, which means at some point it has to cross 1 over G. At that point, it diverges, and that defines TC. So we know that the model with this Cooper instability will describe a superconductor at low enough temperature. Again, it's a strongly correlated system. Then we have to figure out what kind of superconductivity it is giving rise to. Okay, and TC is given by an expression that you can derive. Okay, now the real triumph of the BCS paper is they wrote down the wave function for the ground state. And from that, they're able to get out everything. Now, since we have this hugely solvable model, we should be able to do the same thing, and that's what he did in the first paper. Okay, with BCS, there are only two kinds of occupancies in the normal state, either empty or doubly occupied. And that's why the wave function just has two parameters. Because this wave function, when there's no superconductivity, has to describe the normal state. Okay, and this is the wave function that they chose, and it works beautifully. Okay, now in our case, we have three different occupancies. So we have to have at least three parameters. Okay, no problem. It's not 15, it's 3. Okay, so we can go and solve that problem. We use this wave function, the same, so this describes the empty sector, the doubly occupied sector, and the singly occupied sector. Okay, so now you go and simply variationally solve all of the equations. The key thing you get when you go and do this is you have an equation for the gap. Okay, and you do that, you get a gap equation. Here it is. Okay, and W is the width of the bands. Okay, so you can get this out. Now, because this problem is ultra solvable, we can also get the free energy. You know all the states, we can easily go and do that. And what is curious is the following. So this is the free energy at some temperature. This is a function of the pairing gap that forms. And what you find is there's nothing going on for T for a sufficiently large temperature. If you're right at the temperature where you start to form a condensate, there's a degeneracy between this point and this point. In other words, a gap and no gap. And when you have this degeneracy, that means the transition might be first order. Okay? We lower the temperature even further, and this thing moves out, and at some point there's a global minimum. The global minimum in the free energy also corresponds to the temperature at which the susceptibility diverges. Okay, and hence this would define the true transition temperature in the system. Okay, we were sort of weirded out by this, that this first order nature of the transition, but then, you know, people started working on this, and this is exactly what this group found. Yeah, there does seem to be this first order nature of the transition. So one of the predictions is, yeah, it seems to be, it could be a first order transition, which would be weird. But this is a strongly correlated system. So there's no necessary reason why all of these correlations should happen at the same time. Okay, there's still a jump in the heat capacity, because in the normal and the superconducting states, you can have different things going on. Okay, the energy is changing. Okay, so here's the jump in the heat capacity. Okay, now, it's not sufficient to say you solved the problem by just knowing the ground state. You have to elucidate what are the excited states in the system. And that's what BCS did beautifully. At finite temperature, they're excitations. And in BCS, those excitations are linear combinations of particles and holes. These are these Bogolubov excitations, and the way you construct them is, so these are, they're on the BCS state, they have some probability of existing at finite temperature. And the way you construct them is that you find an operator. Okay, yeah, right. So let me just, yeah. So then these things have some gap. Okay? The way you construct these is this. You know that there are none in the BCS state because that is the ground state. Okay? So you find an operator that annihilates the BCS state. And that will be, this is the condition, and that will be the operator that defines your quasi-particle excitations. And for BCS, that operator is this thing right here. It's just a linear combination of a whole and a particle with these coherence factors. Our problem is fundamentally different. We don't have any such thing as simple as a whole and a particle in the normal state. We have these composite excitations which give rise to the lower and the upper Hubbard bands. So we would not expect our quasi-particle excitations of this strongly correlated superconducting state to look anything like this. They don't. They involve those funky operators that I defined before. Okay, we call these things pions because that's the way our initials were in the first paper. Okay, and here they are. These are the things which annihilate our new wave function. And they involve the composite excitations for the lower band. So it's the whole and the particle excitation for the lower band and the upper band. Which means both the lower band and the upper band now are going to be gapped with these funky objects. And I'll show you what this looks like. Okay, in BCS, the moment you form a gap, this is what happens. And the stuff below and above looks identical because of the particle-hole symmetry in a BCS or a Fermi liquid state. It can't be anything else. Our system fundamentally has an asymmetry. And as you see, there is this, the spectral weight is not the same. So this is one of the comparisons we are trying to do right now. We just got the data from the Stanford group, and we're going to compare these line shapes to see if, in fact, they are the same. But this is a big prediction that there's an asymmetry in the spectral weight in the superconducting state, the particle and hole branches when you open a gap. Okay, did I didn't know. Yeah, the pion band, yes, that's right. Okay. Okay, now, because we know that the superconducting state involves the upper band and the lower band, one of the key puzzles that I've been obsessed about, and that's absolutely what I have been about, is the fact that there's a color change when these materials superconduct. And what they mean by that is this. If they look at the spectral weight, so you integrate the optical conductivity from 0 up to some number, let's say 1 eV, and you look at the spectral weight from 1 eV up to 2 eV, if anything is a low energy property of a system, it should be the superfluid density, but it's not in the cuprates. Because it turns out there's a transfer of spectral weight from here to here when the system superconducts. Okay, and that's the color change. Okay, and here's what they see. This is the low energy weight, this is the high energy weight. This thing is going down, and as the moment it superconducts, there's an accelerated transfer into the lower energy part. Okay, now why would you have a transfer spectrum between a high energy thing and the low energy part if the system is superconducting? Okay, that's always been the mystery, and it's not a big number. This change is roughly 3%. But the reason why this is significant, and this is an example of UV-ion mixing. That's how I started doing ADS, precisely because of things like this in condensed matter. They said that this is enough to explain the condensation energy, why the system is superconducting in the first place. Okay, so what we decided to do is just add up the weight in the lower band and note how asymmetrical this weight is, the particle and the whole branches. Okay, in fact, this is about twice as much as this. So that's the effect we are looking for when we analyze the experiments. Okay, so the key thing here is this weight is positive, and for any reasonable value, okay, so any reasonable value starts with a 1, okay, and sorry, it's back. Okay, yeah. right? Any reasonable value of this, it first of all, it decreases as you crank up U over T, which means it's related to transfer of spectral weight between the two bands. And it's not, if you pick a number, we don't know exactly what this number is, but it's not like, it's off by very much. You pick a reasonable value, something slightly bigger than 1. And what you see is it's on the order of 2 or 3%. Why? It's this dynamical mixing between the two bands. When you turn on the Cooper term, the potential in the kinetic terms, the lack of commutativity is even worse, which means that you're increasing the dynamical mixing between the two bands. Okay? Okay. Now, the last thing we can calculate, and this is what the referee said you have to go and calculate for us to accept your paper, is the superfluid density, and we could easily do that. This is what it looks like in for the free particle system that BCS did. It has to be 0 on either end where you are at the band insulator, and it's some maximum in the middle. The Mott system, it's still 0 at either end, but it also has to be 0 in the middle, okay? Which means this is suppressed relative to the value in the BCS case. And the suppression of the superfluid density is well known in the cuprates. We say it's happening because of Mottness. The proximity to this point where it's an insulator is the reason why this thing is suppressed. Okay. And then you can calculate this as a function of temperature. Okay, rather than bore you with all the things that are different about this than BCS, let me just list them and also bore you. So here you go. This is the observable. BCS, you start with Fermi liquid theory. This is PYHZ superconductivity from the HK or HK family of models. And all of these things are fundamentally different than what's going on over here. Even the kinds of quasi-particle excitations, if you can call them that, because these are quasi-composite particle excitations. These are pions now. Everything is fundamentally different. There's no Hebel-Slichter peak. And this ratio is infinite as opposed to 3.52. So this is a very different superconductor. It makes sense because the system is strongly correlated, and you wouldn't expect anything from Fermi liquid theory to carry over. Okay, so when you break Fermi liquid theory by breaking Z2 symmetry, this is the flow diagram now. There is a new fixed point, and my claim is, even if you were to add Hubbard to HK, you wouldn't flow away from HK. Okay, now I haven't done the calculation because it's impossible to do. Can you start with Hubbard and see that you flow into HK? I don't know how to do that, but I know an argument which would tell me you can't get anything different. It's an argument I can't go into right now, but this is what you find. Anything local flows you in here, including Hubbard, and the superconductor you end up with is very different from the standard BCS superconductor. You constructed a wave function, the finite temperature excitations, and none of it looks like that. Which means that in the evolutionary process of going from a Fermi gas to a Fermi liquid to a BCS superconductor, the terminus of this evolution is Sir Neville Mott. Thank you.
Thank you very much.
Yes.
Have you had a chance to speak with Bob Laughlin to get his?
Okay, I will be
take on
going
this?
next semester.
Yes.
I'll be going to Stanford. Okay. For this semester, it's the East Coast. I'm going to Princeton in 3 weeks, and Bob Laughlin next semester.
Is he still holding firm in his?
I don't know. I mean, the last paper he wrote on the cuprates was a Hartree-Fogg paper. A2 Bob? I mean, it's like, I mean, Bob was always one of the people I looked up to. You know, he had the deepest thoughts. You know, he was like, he did it. You know, I'd say that's just not doing it, Bob. It's just not. David.
Okay, so what makes the model solvable
Yes.
is that the interaction Hamiltonian is local in momentum space.
Yes.
Yeah, and I can't think of how that works. How can I have an interaction that's local in momentum?
Okay, very good point. Everyone says this. Okay.
And me too.
Good. Yeah. You're with everyone. I'm sure that's a question Bob Laughlin will ask me. Okay? Okay. Let me give you a field theory answer. We know about theories because of their correlation functions. Okay? And if I have all the endpoint functions, I know everything about the theory. But I can construct the theory just from the correlation functions. This is the Wakeman reconstruction theorem. All the correlation functions in HK are local. So just by inspecting the operator content of the theory does not tell you if the theory is local or not. Okay, I can define it. Let me give you an example of this.
So should I be thinking of like lots and lots of defects in
No. You should be thinking that. I think at this point you need to think about it much more abstractly. Okay. I don't know what is the mapping which makes the HK model local, but I know it has to have a local description because the correlation functions are all local. Okay, but I think what you really need to think about is that HK is a fixed point. So it's like no one ever argues that, no one ever says, well, you went and treated copper, but you didn't treat zinc. I mean, that's just ludicrous, right? They're both Fermi liquids. They might have slightly different, strengths of interactions, dielectric constants, but it's the same thing. I think we need to think about universality here. What makes Mott insulation special? It breaks the Z2 symmetry. Pick the model that breaks that symmetry and you're done. Because that's the way physics works. If you want to argue anyway else, then you're not doing physics. That's my contention. Okay? It might not look like what you wanted, but you can't argue with a fixed point.
You're looking at me like I disagree.
Well, okay. So let me give you an example. Okay. Say I have a theory that looks like this. Yeah. Okay. It's a quadratic theory with the Laplacian raised to a fractional power. Okay? And you say, oh my God, this is a non-local theory. Okay? This is the fractional Laplacian. Well, here's how I can make this theory local. Okay? If I simply let phi go to minus delta to the gamma minus 1 over 2 times phi, let me see if I got this right. Sorry.
You get the idea.
Yeah, you get the idea. Yeah, that's right. Okay? With a field redefinition, this is completely local. So the operator content of a theory cannot tell you, you need to look at the correlation functions or the entanglement entropy. And that's how we discovered this, actually. Because someone wrote a paper in which, as far as we could tell, it had the same level of non-locality. It was either this operator or e to this operator. This is a paper by Lee and Takinagi. And they had completely different entanglement spectra. We were trying to figure out why is that? As because one theory, you can remove the non-locality, in the other theory, you cannot. Okay, so there's something we don't understand yet about this model, but I have no doubt that it has a local description.
Yeah, I was intrigued by the sort of new superconducting state that you get out of this, in the sense that sort of on a very naive level, when I looked at it, it seems that you're making superpositions of even and odd parity sort of states. Because
Okay.
you're adding, like, let's say, two creation operators in superposition to one and in superposition to zero.
Right.
So this violates, at least on this naive level, the super selection rule that you only have superpositions of
Okay, so
equal parity states.
let
So is there something-
me tell you something. Immediately after we wrote this, someone picked up on this and they said, this is an example of a topological superconductor. Okay, and we got busy doing other things, answering other objections that people had, and we never got back to this. But it's something now that we understand more about topology that we're going to look at.
Yeah, because the naive thing looks like if you take the
Yeah, I know,
superconductor and I
know.
rotate it over 360 degrees, there's now something I can measure that's different about it.
Right, so their point was that you can define a parity operator,
Oh.
and the HK superconductor seems to have non-zero parity.
Or, yeah, exactly.
Right.
So now your
Okay.
superconductor is really funky.
Yeah. So that's a very, very good point.
Would that give Kappa-Toolnik's time reversal breaking?
You know, I only comment on what I've calculated, and I don't know anything about that.
Okay.
So,
Okay,
I
we'll see.
mean, I take the conservative approach.
Any further questions? If not, we'll go to have some drinks.